We'll be starting with the second chapter in physics, class 10th. Chapter 10, The Human Eye and the Colorful World. Let's get started. You have studied in the previous chapter about the refraction of light by the lenses. Okay. You have also studied the nature, position, and relative size of the images formed by the lenses. How can these ideas help us in the study of the human eye? Okay, the human eye uses light and enables us to see objects around us. It has a lens in its structure. What is the function of the lens in a human eye? How do the lenses used in spectacles correct the defects of vision? Okay, let us consider these questions in this chapter. We have learned in the previous chapter about light and some of its properties. In this chapter, we shall use these ideas to study some of the optical phenomena in nature. Okay? We shall also discuss about the rainbow formation, splitting of white light, and the blue color of the sky. So let's get started with the human eye. The human eye is one of the most valuable and sensitive sense organs. It enables us to see the wonderful world and the colors around us. On closing the eyes, we can identify objects to some extent by their smell, taste, or sound they make, or by touch. It is, however, impossible to identify colors while closing the eye. Thus, all the sense organs, the human eye, thus, of all the sense organs, the human eye is the most significant one as it enables us to see the beautiful, colorful world around us. The human eye is like a camera. Its lens system forms an image on a light sensitive screen called the retina. Light enters the eye through a tiny membrane called the cornea. It forms the transparent bulge in the front surface of the eyeball as shown in figure 10.1. So this is figure 10.1. If you see this bulge here, this bulge, that's the cornea and it's transparent. So if you look at somebody's eye, you might find it like shining or something like that. That's due to the cornea. It forms the transparent bulge on the front surface of the eye as shown in figure 10.1. The eyeball is approximately spherical in shape with a diameter about 2.3 centimeters. Most of the refraction of light rays entering the eye occurs at the outer surface of the cornea. The crystalline lens merely provides the finer adjustment of focal length required to focus objects at different distances on the retina. Okay? So, most of the refraction of light rays entering the eye occurs at the outer surface of the cornea. What else? We find a structure called the iris behind the cornea. Iris is a dark muscular diaphragm that controls the size of the pupil. We find a structure called the iris behind the cornea. Iris is a dark muscular diaphragm that controls the size of the pupil. The pupil regulates and controls the amount of light entering the eye. Okay? The eye lens forms an inverted real image of the object on the retina. The retina is a delicate membrane having enormous number of light sensitive cells. The light sensitive cells get activated upon illumination and generate electrical signals. These signals are sent to the brain via the optic nerve. One more question right here. The brain interprets these signals and finally process the information so that we perceive objects as they are. So the eye lens forms an inverted real image on the object on the retina. Retina is a delicate membrane having enormous number of light sensitive cells. The light sensitive cells get activated upon illumination and generate electrical signals. These signals are sent to the brain via the optic nerve. The brain interprets these signals and finally processes the information so that we perceive objects as they are. So now let's look at this image and try to understand where things are. This thing over here, this screen, is the retina. Okay, and this is the optic nerve through which the image formed here gets transported into the brain. Okay, this is the cornea, and when light enters the eye, it gets refracted from the cornea. Okay, and this is these are the ciliary muscles. The ciliary muscles stretch and relax the eyelids. Okay. The eyelids, and this whole thing right here is the pupil. Okay, and this dark colored membrane, in this diagram only, that's iris, and iris is a membrane that gives color to our eyes. Okay, this is a crystalline lens. Okay, and this liquid over here is the aqueous humor. It also provides nutrition to the eye. What else? This is the vitreous humor. Okay, that helps the aqueous humor, and the vitreous humor helps the eye maintain its spherical shape. Okay, I think that's all here, right? We discussed cornea, iris, pupil, aqueous humor, crystalline lens, ciliary muscles, retina, optic nerve, and vitreous humor. Okay. Power of accommodation. The eye lens is composed of a fibrous jelly-like material. Its curvature can be modified to some extent by the ciliary muscles. Can you tell what that thing is? It is the crystalline lens. Okay, this thing is what we are talking about right now. The change in curvature of the eye lens can thus change its focal length. Okay, when the muscles are relaxed, the eye lens becomes thin, thus its focal length increases. Okay, this enables us to see the distant objects clearly. When you are looking at objects closer to the eye, the ciliary muscles contract. This increases the curvature of the eye lens, and the eye lens then becomes thicker. Consequently, the focal length of the eye lens decrease. Okay, this enables us to see the nearby objects clearly. Now, this paragraph can come in the form of many questions. Which muscles help in increasing the focal length or decreasing the focal length of an eye lens? This can be 1-mark question. The answer is ciliary muscles. Explain how the focal length of the eye lens changes. Okay, that's a 5-mark question. And still, you could say this paragraph and then get the answer correct. Explain what is the power of accommodation. That is the next paragraph. Now, one thing that I have observed is the fact that this paragraph can lead to some confusions. Okay, by reading this, you will not understand how when the lens becomes thin, its focal length increase. If a lens is thin, most people would think its focal length is supposed to decrease. Okay, but the thing is, when the lens becomes thin, Okay, when the lens becomes thin, and it was like this before. Okay, it was like this. How is the focal length defined? Can anybody say how the focal length is defined? See, this lens will be a part of a circle, okay, and we cut this out of the part of the circle. Basically, if you check, there will be a bigger circle like this. Okay, and the center here is 2f1, so f1 will be there. Now my diagram is completely wrong. Okay, but if the curvature is increased, check that the circle that the lens is a part of will be also small. So this will be 2f1 and this shall be f1. This is the difference. Okay, so we got a circle like this and we got a circle like this. See, there's a difference in curvature in this and this. Okay, this has more curvature than this one. Okay, and due to that fact, this lens will be thinner than this lens over here. This will be thinner than this one. Okay, and now also assume that there is another circle that makes this part of the lens. Okay, now due to this, if you check, this is 2f1 and this is f1. This is 2f1 and this is f1. Therefore, if the thickness if the lens is thin, that means the curvature is less. If the curvature is less, that means the focal length will increase. Okay, got it? I hope you did, because this part is very confusing. To be honest, I was confused too on why, but then I drew it and then I understood what's going on. Now the next point can be asked for 1 mark questions. The ability of the eye lens to adjust its focal length is called power of accommodation. So it is accommodating to different things at different distances. However, the focal length of the eye lens cannot be decreased below a certain minimum limit. Okay, try to read a printed page by holding it very close to your eyes. You may see this image being blurred or feel strain in the eye. So what you can do right now is you can pause this video. You can bring the device that you're seeing this video in close to your eyes and try this yourself. Okay, this is basically the textbook, so you can read it. You may see the image being blurred or feel a strain in your eye. To see an object comfortably and distinctively, you must hold it about 25 centimeters from the eye. The minimum distance at which objects can be seen most distinctively without strain is called the least distance of distinct vision. 1 mark question. What is least distance? What is least distance of distinct vision, or the near point of the eye, as you can see here? The minimum distance at which objects can be seen most distinctively or without strain is called the least distance of distinct vision, or the near point of the normal eye. For a young adult with normal vision, the near point is about 25 centimeters. Question. I think this could be for a 2 mark or 3 mark question. What is the least distance of distinct vision, or near point of the human eye, and what is the value of it. So you can say the definition, and then you can say the near point, which is 25 centimeters. The furthest point up to which the eye can see objects clearly is called the far point of the eye. It is infinity for a normal eye. Okay, 1 minute. Great. Sometimes the crystalline lens of people at old age becomes milky and cloudy. This condition is called cataract. It causes partial or complete loss of vision. It is possible to restore this vision using cataract surgery. Now, this takes about 10 minutes or something. It's very quick. The cataract surgery, my grandma had it, and we gave her the cataract surgery. And what it does is basically remove the crystalline lens and attach a new artificial one. It takes about 4 to 5 weeks to adjust to the new lens. Okay. Defects of vision and their correction. Now, there are some things in the defects of vision that I can relate to. Sometimes the eye may gradually lose its power of accommodation. In such conditions, the person cannot see the objects distinctively and comfortably. The vision becomes blurred due to the refractive defects of the eye. There are mainly three conditions, three common refractive defects of visions. Okay, these are myopia or nearsightedness, hypermetropia or farsightedness, and presbyopia. The best thing that you could do is, if the question is asked, you can also add this cataract into it. These defects can be corrected by using the suitable spherical lens. We discuss below these defects and their corrections. Myopia. Myopia is also known as nearsightedness. A person with myopia can see nearby objects clearly but cannot see distant objects distinctively. Okay, a person with this defect has the far point nearer than infinity. Such a person may see clearly up to a distance of a few meters. In a myopic eye, the image of a distant object is formed in front of the retina, okay, and not on the retina itself. So, if you see, this is the far point of a myopic eye, that is not infinity. But if the object is at infinity, as you can see, this converge here, that is at this point. Okay, and here's the correction for myopia. We shall read about that. This defect may arise due to two reasons, that is the excessive curvature of the eye lens, okay, or the elongation of the eyeball. This defect can be corrected by using a concave lens of suitable power. This is illustrated in figure 10.2 C. A concave lens is of suitable power will bring the image back to the retina, and thus the defect is corrected. So if you see, when the object was at infinity, our eye converges it before the retina and it gets all messy, right? But if it is if we are using a concave lens, then the concave lens already diverges the light rays just before it reaches the eye, so that when we converge it again, it shall reach in the correct position. Okay, so this is also a practical question, because if we want the objects to converge here and it converges here, Okay, let's say that the image is formed there. What we could do is first converge it using a concave lens, diverge it using a concave lens, and then converge it, and it will reach the screen like this. It's a more practical thing. Okay, so there is a great distinction between the far point of a myopic eye and a normal eye. As you see, infinity is way more than a few meters. Okay. This entire paragraph is actually important. And try to write the reasons in paragraphs rather than like this given in the textbook, because the beauty is also checked in the board exam papers, and if your paper is kind of beautiful, most teachers will just not even look at it. Well, that's what we've been taught. Now, to tell you the truth, I can kind of understand myopia because I am myopic. Funny part. Hypermetropia. Hypermetropia is also called farsightedness. A person with hypermetropia can see distant objects clearly but cannot see the nearby objects distinctively. A near point for a person is the farthest away from normal near point. Okay, let me read this again. The near point for the person is farthest away from the normal near point. Such a person has to keep a reading material much beyond 25 centimeters from the eye for comfortable reading. This is because the light rays from a close by object are focused on a point behind the retina as shown in figure this one. We shall do that. Now, this defect arises either because the focal length of the eye lens is too long or the eyeball has become too small. This defect can be corrected by using a convex lens of appropriate power. This is illustrated in figure 10.3c. Eyeglasses with converging lenses provide additional focusing power required for forming the image on the retina. Yeah. This entire paragraph is quite important because 1 mark questions can be asked from here also, like which lens is used for correcting myopia. A question like that can be asked. It is concave, and which is used to correct hypermetropia, that is uh, convex. Why convex? That's a question. See, this is the normal far point, as you can see here. Normal far point for a hypermetropic eye, and it forms on the retina. All good. Now here's the thing. If the object is moved here, that is the normal near point for a human eye, the hypermetropic eye will form the image behind the retina rather than in front of it. Okay. Now what do we do? See, this is the lack of converging it. Okay, lack of properly converging it. What you can do is already converge it and then further converge it by the eye lens. So put a convex lens. Okay, that's it. You shoot two rays like this, it is already converging, and you further converge it using the eye lens. That's all. It's nothing special in it. This is easy. Um, Also, a few more things to note here is that if you trace back these, then you'll see that you get the far point. The image is formed at the far point of the what hypermetropic eye, uh, not myopic eye. If you just retrace these rays that diverge, okay, if you do that, you'll see that the image is formed at the far point of the myopic eye. Okay, that is what can we say this, the person thinks that the object is there rather than at infinity. That's all. And in the case of hypermetropic eye too, if you retrace these, sorry, if you retrace these, then you'll see that this forms at the near point. This image here forms at the near point of a hypermetropic eye. Okay, that is the person thinks that the object is there. Now, yeah, that's all. Now, presbyopia, the power of accommodation of the eye usually decrease with aging. For most people, the near point gradually recedes away. They find it difficult to see nearby objects comfortably and distinctively without corrective glasses. This defect is called presbyopia. Question: what is presbyopia? The power of accommodation gradually loses by aging, and they find it difficult to see nearby objects without corrective eyeglasses. This is called presbyopia. This can occur due to it arises due to the gradual weakening of the ciliary muscles and diminishing flexibility of the eye lens. Sometimes a person may be suffering from both myopia and hypermetropia, like my mom and dad. Such people often require bifocal lenses. A common type of bifocal lenses consists both the concave and convex lenses. Okay. Uh, Now, the upper portion consists of a concave lens. It facilitates distant vision, and the lower part is a concave lens. Sorry, convex lens. It facilitates near vision. Okay. Now we are looking at some phenomena of light, and this entire paragraph is for eye donors. So that is, you can donate your eye to people who are blind, and there are about 35 million people developing in the developing world are blind. Okay, and 4.5 million people are corneal blindness, and it can be cured by the corneal transplantation of donated eyes. Okay, and out of this 4.5 million people, 60% are children below the age of 12. We can give this, and it can be given by people who belong to any age group or sex. There is no issue. People who have spectacles or any diseases that is not communicable. Okay. The eye must be removed within 4 to 6 hours after death. Okay, and you need to inform the nearest eye bank immediately. Okay, so the eye bank will remove the eyes. Okay, and it takes about 10 to 15 minutes. And people who died of AIDS, hepatitis B or C, rabies, acute leukemia, tetanus, cholera, meningitis, or encephalitis, they cannot donate because it's communicable. Okay, that's all. Refraction of light through a prism. Now you have learned how how the light gets refracted through a glass slab in the last chapter. Okay, for parallel refracting surfaces, as in glass slab, the emergent ray is parallel to the incident ray. However, it is slightly displaced laterally. How would light get refracted through a transparent prism? Consider a triangular prism. It has two triangular bases and three rectangular lateral surfaces. Okay. These surfaces are inclined to each other. The angle between its two lateral faces is called the angle of the prism. See, this is the angle of the prism. Let us now do an activity to study the refraction of light through a triangular glass prism. So let's see this activity. Fix a sheet of white paper on a drawing board using drawing pins. Place a glass prism on it in such a way that it rests on its triangular base. Trace the outline of the prism using a pencil. Draw the straight line PE inclined to one of the refracting surfaces, say AB of the prism. AB is here and PE is something that is incident on this side AB. Now, what else next? Fix two pins, say at point P and Q, on the line PE as shown in 10.4. P and Q. Okay. Isn't it? Okay. Look for the image of the pins fixed at P and Q through the other face of AC. Okay. Fix two more pins at the points R and S such that the pins at R and S and the image of the pins at P and Q lie on the same straight line. Okay, it kind of makes sense. There we go. Kind of makes sense. Remove the pins and the glass prism. Great. The line PE meets the boundary of the prism at point E. The line PE meets the boundaries of the prism at point E. Okay. Similarly, join and produce the points R and S. Let these lines meet at the boundary of the prism E at E and F respectively. Join E and F. Draw perpendiculars to the refracting surfaces AB and AC of the prism at points E and F respectively. So like this. Okay. Mark the angle of incidence I and the angle of refraction R and the angle of emergence as shown in 10.4. So this angle is angle of incidence and this angle is angle of refraction and this angle is the angle of emergence. Okay. Now if this light ray was to continue like this, it shall go on like this. And if this ray of light was normal and it's not refracted or it's not an emergent ray, then the original light ray will be like this. And this angle over here, angle D, is called the angle of deviation. Okay, important. Here, PE is the incident ray, okay, EF are the refracted ray, and FS is the emergent ray. You may note that a ray of light is entering from air to glass at the first surface AB and the light ray on the refraction has bent towards the normal. Okay, at the second surface AC, the light ray has ended from glass to air. Hence, it has bent away from the normal. Compare the angle of incidence and the angle of refraction at each retracting surface of the prism. Okay, is this similar to the kind of bending that occurs in a glass slab? The peculiar shape of the prism makes the emergent ray bend at an angle to the direction of the incident ray. Okay, this angle is called the angle of deviation. In this case, angle D is the angle of deviation. Mark the angle of deviation in the above activity and measure it. So, question, what is the angle of deviation? The peculiar shape of the prism makes the angle of emergent ray bend at an angle to the direction of the incident ray. This angle is called the angle of deviation. Okay. Dispersion of white light by glass prism. You must have seen and appreciated the peculiar colors in a rainbow. How could the white light of the sun give us various colors of the rainbow? Before we take up this question, we shall first go back to the refraction of light through a glass prism. The inclined refracting surface of a glass prism show exciting phenomenon. Let us find out through an activity. So, activity 10.2, take a thick sheet of cardboard and make a small hole or narrow slit in the middle. Allow the sunlight to fall on the narrow slit. This gives a narrow beam of white light. Now take a glass prism and allow the light from the slit to fall on one of its surface as shown in figure 10.5. This is figure 10.5. So the white light, there shall be this cardboard and there's a slit here through which the narrow beam goes to the glass prism and it breaks down into several colors. Okay. Turn the prism slowly until the light that comes out of it appears on a nearby screen. Now, what do you observe? You will find a beautiful band of colors. Why does this happen? The prism has probably split the incident white light into a band of colors. Note the colors that appear at the two ends of the color band. What is the sequence of colors that you see on the screen? The various colors seen are violet, indigo, blue, green, yellow, orange and red. Okay, as shown in figure 10.5. So basically here, check. The acronym VIBGYO will help you remember the sequence of colors. So violet, indigo, blue, green, yellow, orange, red. VIBGYO. The band of colors, the band of the colored components of a light beam is called its spectrum. Okay. You might not be able to see all the colors separately, yet something makes each color distinct from the other. The splitting of light into its component colors is called dispersion. What is dispersion? The splitting of light into its component colors is called dispersion of light. Okay. Now, there is a lot of dispersion, so it is important to say dispersion of light. It may be dispersion of seeds also. Okay. So you have seen that white light is dispersed into 7 color components by a prism. Now, why do we get these colors? Different colors of light bend through different angles with respect to the incident ray. As they pass through a prism, the red light bends the least while the violet the most. Thus, the rays of each color emerge along the different paths and thus becomes distinct. It is the band of distinct colors that we see in a spectrum. Okay. Now, Sir Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. He tried to split the colors of the spectrum of white light further by using another similar prism. Okay. However, he could not get any more colors. He then placed the second identical prism in an inverted position with respect to the first prism as shown in figure 10.6. So if you see, this is our first prism that split the violet into its 7 different colors. Now it's represented by only 2, don't worry. And then he went ahead, and mad scientist, he experimented by putting it upside down. Okay, the prism is now upside down. The red light continues to go on, but now it refracted like this, and the white light also, it went like this. They join together here, not white light, violet light. They join together here and it will become white light. Why? Is red and violet going to add up to white? No, there's a lot more colors here. Okay, a lot more colors, and these lot more colors go here too, and all those lot more colors once again refract, they join, and then white light comes out. Okay, the whole story does not revolve around red and violet. There are lights, there are other colored lights in between, but we are not just representing them, that's all. Okay, now this allowed the colors of the spectrum to pass through the second prism. He found a beam of white light emerging from the other side of the second prism. This observation gave Newton the idea that the sunlight is made up of 7 colors. Any light that gives a spectrum similar to that of sunlight is often referred to as white light. Okay, a rainbow is a natural spectrum appearing in the sky after a rain shower. Okay, it is caused by the dispersion of sunlight by tiny water droplets present in the atmosphere. A rainbow is always formed in a direction opposite to that of the sun. The water droplets act like small prisms. They refract and disperse the incident sunlight, then reflect it internally, and finally refract it again when it comes out of the raindrop. Okay, due to the dispersion of light and the internal reflection, different colors reach the observer's eye. So basically what happens is that the sunlight, they split. Okay, they split inside the water droplet, and they reflect again. Okay, reflect again and hits the other boundary of the water droplet, and then refract again. Okay, this is what happens. Also, as I said, there is other colors also, and there is a name for this property where the light gets reflected out of the other surface rather than just coming out. That is called total internal reflection. Now you may have a question, but if it is the case of a glass prism, it just goes in, completely refracts into all the different colors and gets out. But why is it this case in the water droplet? Why doesn't this happen in the water droplet? The thing is the difference in shape. That's the key thing. The sunlight, it goes and hits the water droplet in an angle. Okay, and there is something called the critical angle, which is 48.6 degrees in water droplet. Now the sunlight, it goes in and hits it more than its critical angle, and therefore it does total internal reflection and then gets refracted. More information about the critical angle will be on class 12th. Now important in these paragraphs, lots of questions can be asked, so I cannot specifically say what the questions are, just like in social science or something like that. Okay, like who tried to split the white colors again? Who tried to split the spectrum again? That's Sir Isaac Newton. Okay, at the same time, you might be asked how the this works. Okay, how we can obtain white light again from using the two prisms. So there is not a definite question that comes from a paragraph. You cannot say this question will come from this paragraph in science. That's the issue. You can also see a rainbow on a sunny day when you look at the sky through a waterfall or through a water fountain with the sun behind you. The next thing that you're going to see is the atmospheric refraction. Oh yeah, and this one can also come. So there are many important points, okay, and also remember this one. The band of colored components of a light beam is called its spectrum. You might also be asked about spectrum, so also know that. And yeah, let's continue with atmospheric refraction. And there's only 2 more pages left as I remember it. I don't know. So you might have observed the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. Basically, just look at petrol. That's it. Okay, when you're filling petrol, just look at things. If there is petrol somewhere, like in a gas tank, the air shall be hot, okay, and if you look through that, things behind it will flicker or seem blurry or things like that. So the air just above the fire becomes hotter than the air further up. The hotter air is lighter than the cooler air above. It has a refractive index slightly less than the cooler air. Since the physical conditions of the refracting medium is not stationary, the apparent position of the objects as seen through the hot air fluctuates. This wavering is thus an effect of atmospheric refraction, okay, of light by the Earth's atmosphere or on a small scale in our local environment. The twinkling of stars is a similar phenomenon on a much larger scale. Let us see how we can explain it. So this diagram, if you see it, it's confusing. Okay, and I'll draw it so that you can understand. Imagine you are here, okay, and a star is there, and this is the layers of atmosphere. Okay, now what happens is that this is like this, and there shall be a normal, and the angle reduces, okay, and again the angle reduces, and again the angle reduces so much. It's falling to your leg. Okay, it's like this, and the light rays come and hit your eye. This is not exactly your eye. Let's just increase the size of this. Okay, there we go. Just refracts and draw it backward like this. Your eye will think that the star is at this location. Really, it's at this location, but your eye will think that the star is at this location. Okay, this is the real position, and this is the apparent position. That's what they are saying about apparent star position due to atmospheric refraction. See, that's why this is the layers of atmosphere, okay, and in these layers of atmosphere the light gets refracted once more, and again refracted, and to your eye same way, refracted once more, and then again refracted to your eye. Okay, so the atmosphere refracts the light. So, and if you trace it back, you will feel that the star is here rather than its real position that is there. Got it? Now, twinkling of stars. The twinkling of star is due to atmospheric refraction of starlight. The starlight on entering the Earth's atmosphere undergo refraction continuously before it reaches the Earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from the actual position. The star appears slightly higher than its actual position when viewed near the horizon. Okay. Further, this apparent position of the star is not stationary. Okay, it keeps on changing slightly. Since the physical conditions of the Earth's atmosphere are not stationary, as was the case in the previous paragraph. Since the stars are very distant, they're approximately point-sized sources of light. As the path of the rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye flickers. The star sometimes appear brighter and other times fainter, which is the twinkling effect. Okay. Okay, and let's do this. The twinkling of stars is due to atmospheric refraction of the starlight. The starlight on entering the Earth's atmosphere undergo refraction continuously before it reaches the Earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from its actual position. The star appears slightly higher than its actual position when viewed near the horizon. Okay. Further, this apparent position of the star is not stationary but keeps on changing slightly. Since the physical conditions of the Earth's atmosphere are not stationary, as was in the case of the previous paragraph. Since the stars are very distant, they are approximate point-sized sources of light. As the path of rays of light coming from the star goes on varying slightly, the apparent position of the stars fluctuates and the amount of starlight entering the eye flickers. The star somewhat appears brighter and stars sometimes appear brighter and the other times it is more fainter, which is the twinkling effect. Now if you see, due to the same reason, this is the horizon and this is the sun. And now the thing is, to your eye the sun might be here when the sun is actually here. Okay, that's why there is a 2-minute delay in the sunrise and sunset. We shall read about it here. What I said was wrong. I will correct it. So why don't the planets twinkle? The planets are much closer to the Earth and are thus seen as extended sources. If we consider a planet as a collection of large number of point-sized sources of light, the total variation in the amount of light entering our eye from all the individual point-sized objects will average out to 0, therefore nullifying the twinkling effect. Direct questions of this has been asked in the board exams. Therefore, this is quite important if you want, if you want good marks in it. Advanced sunrise and sunset. Sunrise and delay in sunset. Okay, so the sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction. By an actual sunrise, we mean the sun actually crosses the horizon. Okay, actual crossing of the horizon by the sun. 10.10 shows this. 10.10 shows the actual and apparent position of the sun with respect to the horizon. The time is different between the actual sunset and the apparent sunset for about 2 minutes. The apparent flattening of the sun's disk at the sunrise and the sunset is also due to the same phenomena. Okay, that's it. The scattering of light. The interplay of light with objects around us gives rise to several spectacular phenomena in nature. The blue color of the sky, color of water in deep sea, and the reddening of the sun at sunrise and sunset are some of the wonderful phenomena we are familiar with. In the previous classes, you have learned about the scattering of light by colloidal particles. The path of a beam of light passing through a true solution is not visible. However, its path becomes visible through a colloidal solution where the size of the particles are relatively larger. Tyndall effect. The Earth's atmosphere is a heterogeneous mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. The light reaches us after being reflected diffusely by these particles. The phenomenon of scattering of light by the colloidal particles gives rise to the Tyndall effect, which we have learnt in class 9th. This phenomenon is seen when a fine beam of sunlight enters a smoke filled room through a small hole. Okay. Thus, scattering of light makes the particles visible. Tyndall effect can be also observed when sunlight passes through a canopy of a dense forest. Here, tiny water droplets in the mist scatter light. Now I'm thinking everything in the textbook is now to be marked. Okay, there is not even any jokes or something like that. We first thought that Bujo was very Bujo was very annoying in our textbook. You know, that character that asks a lot of questions. We thought that it was annoying, but now we kind of miss him. The color of scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of larger size scatter light of longer wavelengths. The size of the scattering particles is large enough then the scattered light may even appear white. Now, before I continue, I would like to say that violet has the least wavelength while red has the longest wavelength. And if the wavelength increases, then the bending also decreases. Okay. Why is the color of clear sky blue? The molecules of air and other finer particles in the atmosphere have sizes smaller than the wavelength of visible light. These are more effective in scattering light of shorter wavelengths at the blue end rather than light of longer wavelengths at the red end. Okay. The red light has wavelengths about 1.8 times greater than the blue length. Thus, when the sunlight passes through the atmosphere, the fine particles in air scatter the blue color, shorter wavelengths more strongly than red. The scattered blue light enters our eyes. Okay. If the earth has no atmosphere, then there would not have been any scattering. Then the sky would have looked dark. The sky appears dark to passengers flying at very high altitude, as the scattering is not prominent at such heights. You might have observed that danger signal lights are red in color. Do you know why? The red is the least scattered by fog or smoke. Therefore, it can be seen by this in the same color at a large distance. So this is a very important fact. Direct questions are asked in the same paragraph, so you need to read it again. And this is the summary. The ability of the eye to focus on both near and distant objects while adjusting its focal length is called the power of accommodation. Okay, the smallest distance at which the eye can see the objects clearly without strain is called the near point of the eye, or the least distance of distinct vision. For a young adult with a normal vision, it's about 25 centimeters. Now, one more thing, it only says accommodation of the eye, it's actually power of accommodation. Next, the common refractive defects of vision include myopia, hypermetropia, and presbyopia. Myopia, short-sightedness, the image of distant objects is focused before the retina, is corrected by using a concave lens of suitable power. I have it. Okay. Now, hypermetropia, far-sightedness, the image of nearby objects is focused beyond the retina and is corrected by using a convex lens of suitable power. The eye loses its power of accommodation at old age, and that is presbyopia. Convex lens of suitable power. If I said concave, I'm sorry, I don't remember. The splitting of white light into its component colors is called dispersion. The scattering of light causes the blue color of the sky. Okay, that's it, and we can do the exercises later in another video. Thanks for watching, and bye. Also, if you have any questions in this topic, because this topic is very confusing, you can put it down in the comments below. Alright, thanks and subscribe.